Okay, so good afternoon, everyone, and welcome you back to study robotics, automation, and Internet of Things course offered by NTU. And today we move on to study session 4. Session 4 is about the networked sensor, all right? So by now we have completed the study about the robotics, automation, and also the session 3 is about the communication inside IoT. So you remember that the robotics could be considered as a mini version of IoT, and the automation system could also be considered as a version of IoT. So therefore, these three topics are interrelated, all right? So today we will focus on networked sensor, and you will know that the sensor will also contribute to the development of a robot, because inside the robot we have a feedback control system, all right? And the robot's motion are under control. So without the sensor, then we cannot control the motion of the robot. Similarly, inside automation system, we also have a feedback control loop. So inside the feedback control loop, sensory feedback play a very important role. So without the sensor, then we cannot achieve feedback control. So then you will see that today's lecture will also help you to understand better the topics about the robotics and the topics about the automation, all right? So you see all the topics are interrelated, all right? There's no overlapping, all right? And as usual, we can spend a few minutes to do a short Q&A in case if you have a question about the topics that you have studied so far. So you can raise any question which are related to robotics, automation, and communication inside IoT. So you can type your question inside the chat window, or you turn on your microphone, you ask your question. I received one email from one student. He mentioned that he did not understand how come in order to configure communication speed, we need to do the calculation and get the integer part, decimal part, etc. Right? So that is a good question. So actually the answer is very simple, because here we are the user of a microcontroller, all right? So once you put yourself into the user of a microcontroller, you just follow the instruction provided by the designer of a microcontroller. So therefore, we should not ask a question of why, because microcontroller has been designed by the designer in this way, all right? As a user, we just follow the instruction. That's it. It's like when you purchase a car, normally you will never make or make this question of why this car has been designed in this way, all right? Because the car has been designed in this way by the designer. So you buy a car because you want to be the user. So you just use the car, drive the car, okay, by following the instruction of the car. So similarly, when we study the IoT, in particular, the hardware support to IoT, because we make use of a microcontroller, therefore, we must adjust our mindset, put ourselves into the mindset of a user, but not mindset of a student. Because as a student, you can ask all kinds of questions. Why to design this module in this way? Why to design module in another way? All right. So that is the mindset of a student. But here we put ourselves into the mindset of a user because we are going to use microcontroller to support the implementation of IoT or eventually robot and the automation system. All right. So our focus is at the higher level, how to implement, how to design a robot, how to implement, how to design automation system, then how to implement an Internet of Things, which will cover a large area. All right. Okay. So let's answer that question. So follow the instruction. Then in today's lecture, second lecture, it's the same. If you put yourself into the mindset of a student, then you may ask a lot of questions why. It's like later I will tell you for the second lecture, all right? Actually, it's with the price of a bicycle, you get the sport car, all right? And then you may say, I just want to ride a bicycle, but you give me a sport car, okay? Then you should not ask why, because so cheap, all right? But actually, you can drive a sport car like a bicycle. You do not need to drive a sport car like a racing car, but people may drive it as like a racing car. Similarly, for this Cortex ARM microcontroller, all right? So it behaves like a sport car, very, very powerful microcontroller at the extremely low price, all right? You can do simple things. You can also do very complicated things, all right? So keep this mindset of a user in mind, and you will enjoy, okay, the study. All right, if there's no question, then we move on to study today's session. Today, we will study network is the sensor, and you understand that the three pillars underneath IoT include microcontroller, sensor, and actuator, right? So last week we have already studied the nature or basics about the first pillar, which is the microcontroller. So with the use of microcontroller, we can establish a communication network. So you remember with a synchronous communication protocol or methodology, we are able to build a two-dimensional IoT, right? Because each node inside the network could communicate with 4 other nodes, all right? So therefore, with a synchronous serial communication protocol, we can only build up a two-dimensional IoT. Then for the second method, the second method is asynchronous serial communication protocol. So with the asynchronous serial communication protocol, we are able to build three-dimensional IoT. This is because one single node will be able to connect to a neighbor, all right? If one node will be able to connect to 6 neighbors, that should be good enough for us to build up a three-dimensional IoT, all right? So last week we have studied these two basic communication protocol. So with the use of these two basic communication protocol, then you can develop all kinds of IoT, all right? So really, the knowledge technology are very powerful. Now today we focus on the use of sensor, okay, to extend the network of data communication. Because with the communication network, we can only exchange the data. Then you may ask this question, how to obtain the data for communication, all right? Because we need to have a device for us to capture the data from the environment. The answer is what? The answer is a sensor, all right? So sensor will provide the data for the network, okay, to exchange the signal, exchange the information, all right? So today's lecture is also very, very important, all right? So today's session will include 3 lectures. So lecture 1 is for you to understand a little bit about the sensor, all right? So we will cover the most popular sensor in engineering, For example, temperature sensor, humidity sensor. These two types of sensors are very important to our ecosystem, John. When we live in the environment, if the temperature is no good, humidity is no good, then we may not feel comfortable, right? So humidity sensor, temperature sensor are very important. Second one is a velocity sensor, because in the industry and in our dynamic world, right? A lot of dynamic behavior are manifest in the form of motion. When we talk about the motion, there are three important physical quantity. One of them should be velocity, all right? If we know how to measure velocity, then eventually we should be able to know what should be the position, what should be the acceleration, etc. All right? So lecture cover these three type of sensor in engineering. Then second lecture is for us to know how to interface with analog sensor, or how to attach analog sensor into IoT, Internet of Things, all right? Lecture 3 is for you to know how to attach digital sensor into the IoT, all right? Because all the sensor more or less will be categorized into this broad category, analog sensor, digital sensor. If you know how to interface with the analog sensor, how to interface with the digital sensor, it means what? Eventually, you can aid in all kinds of sensor into your network of communication. All right? Okay, so let's start with lecture 1 of session 4. Okay, so in lecture 1 of session 4, we will cover 3 popular sensor in engineering. The first one is a temperature sensor, second one is a humidity sensor, and the third one is a velocity sensor, all right? And then with this understanding, more or less you know what should be analog sensor, what should be digital sensor, all right? Another good news for you to remember is actually microcontroller by default could be considered as a sensor for voltage and a sensor for measuring velocity of a square wave. Okay, so you see, because in the physical world, all right, so we can talk about the electric signal. Among the electric signal, voltage, okay, is a very popular one, all right? So by default, microcontroller is a sensor for measuring voltage. Microcontroller is also a sensor for measuring velocity of square wave. Wave means is a regular wave, okay? It's a time function, okay? So that is a good news to you. If you know how to use the microcontroller, so it means what? You are ready to design any sensor, all right? As long as you know how to convert the value of a physical quantity under measurement into voltage or into square wave form. That's it. Then you just use microcontroller to do, okay, one of these 2 measurements done already. So that is a good news to you, all right? So it means once you know how to use microcontroller, you are ready to become a designer of any sensor in engineering, all right? So that is a good news to you. So you keep this in mind. Therefore, then your focus for the lecture 1 is to know, let's say, how to convert the value of temperature into voltage, how to convert value of humidity into voltage. That's it. Once you have a voltage as an output, then use microcontroller to convert voltage into a readable number, all right, or digital number, all right? Or how to convert velocity of any physical entity into the velocity of a square wave. That's it, because microcontroller can measure velocity of a square wave, all right? So then you understand to study the sensor, actually is quite easier with the use of a microcontroller. All right, okay. So let's look at the first sensor. Then the focus is to know, okay, what is the nature of this physical quantity, then how to convert the value of a temperature into voltage. That's it, all right, okay. So then this video will more or less explain to you what is a temperature sensor and how to do a measurement either manually or automatically, or okay.
They originally needed it for measuring the water temperature in a set of experiments, determining if cold water boils faster than hot. But just for fun, I also got it to turn on this PC fan when the heat was too high. What's a thermistor? The thermistor is usually a ceramic or polymer material with two wires connected to it. The key is that the thermistor's resistance changes with temperature. With some, the resistance increases as the temperature increases. Those are called positive temperature coefficient, or PTC thermistors. With others, the resistance decreases as the temperature increases. Those are called negative temperature coefficient, or NTC thermistors. I couldn't find a thermistor locally, but some quick research turned up that automobile coolant temperature sensors are just thermistors in a protective case, which was a good thing since that saved me having to make a case of my own. With this one, there's only one obvious place to connect to, this threaded part. So where do the two thermistor wires go inside? Well, one goes to the threaded part and the other goes to the brass case. So I wrapped one wire tightly around the case. And after attaching a ring terminal to a wire and finding suitable nuts, I attached another wire to the threaded part. I then connected up a meter and put it on the resistance scale. Remember, the resistance changes with the temperature. I put my fingers on the probe part and it started to heat up. Sure enough, the resistance on the meter started to decrease as the temperature increased. So it contains an NTC, or a negative temperature coefficient thermistor. To be useful, I needed to know what resistance matches what temperature. Unfortunately, I couldn't find a resistance temperature table for this particular one, so I had to make my own. To do that, I prepared a tall container, this soda can with all the paint sanded off. I filled it with water and put the probe part of the sensor in the water. I also put in my kitchen thermometer. The long length of my thermometer is why I went with a tall container. For my purposes, I needed to know the resistance to temperature values for temperatures near the freezing point of water. So I put the whole thing in my freezer until the thermometer read near 0 Celsius, or 32 Fahrenheit. Then I took it out, connected my meter to measure resistance, and put it on my stove heating element. I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius or 212 Fahrenheit. And here's a chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I'd gone through this process was to do some experiments to determine if cold water boiled faster than hot water, as some people think it does, and to find out why that myth might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I cover in another video I'll point out later. Here's the fun I had making a PC fan turn on when the thermistor gets too hot. First, here's the circuit without the thermistor. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with a thermistor. The positive from the power supply goes to one end of the thermistor. The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. But this time, when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, and so it has a high resistance. The fan needs a certain amount of electrical current going through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan. And the resistance of the thermistor is high enough to make that current too low. Now I use this hairdryer to heat up the thermistor. That causes the thermistor's resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Well, thanks for watching.
Okay, so this video also showing you a temperature control system. All right, so we put the thermistor. Now you understand. Thermistor is a special material. When the temperature increase, is the resistance value will reduce. All right, so that is a way for us to convert the value of temperature into electrical physical quantity, such as resistance, capacitance, inductance. Once we know resistance, capacitance, inductance, then we should be able to convert it into voltage or current. I guess all of you have studied physics in year 1, all right? So it's quite straightforward, all right, for us to do the conversion from temperature into voltage, all right? Now let's quickly go through some basic physics which are related to the use of temperature. For example, you may know the equation of ideal gas, all right? So inside a container, if let's say we have a gas, all right, and inside we have a pressure, we have a volume, we have a temperature, we have a certain amount of a specific gas, all right? Then this is the equation of ideal gas. So it tells that the pressure is proportional to temperature, volume is also proportional to temperature, and here in front you have this gas constant. Then the number of mole is a unit of a measurement for the amount of gas inside the container. So this is quite a standard equation in physics, all right? So therefore, with the use of this equation, actually we can do some computation of temperature if we know the value of a related physical quantity. So that is for you to know, okay, how to calculate the temperature, all right? But here our focus is to know how to do the measurement, all right? Another thing is for you to know is a transfer of the heat, how to increase the temperature. Normally we know we must heat or supply the heat to the material. So this equation will tell you in order to change or increase or decrease this amount of temperature for a material with this mass, we must supply this amount of thermal energy. Heat means thermal energy, all right? Then in front is a coefficient, is a specific heat coefficient for this material, all right? So basically this coefficient describes the capability of the material to absorb or release thermal energy, all right? So then another 3 phenomenon for you to know for the transfer of the heat, all right, should be this convection, conduction, and the radiation. I believe in the winter in China, I guess all of you know how to absorb the heat, okay, by your body from the environment. You may have a heater, all right? So radiation is a popular way for us, okay, to heat up our hand in winter, all right? And on top of that, you know, when the heat move inside the material, we call this phenomenon as a conduction, all right? When there's exchange of the heat between 2 different media, for example, one is a solid, another is a gas, okay? In this case, it's a convection. So exchange of a heat between the gas, the air, okay, and the solid, then we call it as a convection. So you see the amount of flow of the heat is proportional to temperature difference, proportional to the area in which the exchange of the heat occurs. Then you have a coefficient, all right? So you just imagine this is a current. So flow of a heat is similar like something like a current, right? And the temperature actually is something similar to the voltage. So once you have a temperature difference, then this difference in temperature will produce a flow of a heat. It's like when you have a voltage difference, the voltage difference will be able to produce a flow of electron. Flow of electron is also called as a current, all right? Then for conduction, so you say for a same rigid body, one side is T1 temperature, another side is T2 temperature. As long as there's a temperature difference, then you will see a flow of heat will pass inside the material, and this flow of heat proportional to the temperature difference, inversely proportional to the thickness of the material, also proportional to the area in which the heat will flow, okay, flow in, flow out. Then in front, you will have a coefficient. So this is an equation very much like a relationship between voltage, current, and resistance. All right, okay. Then for radiation, is the same law. If this is the source temperature is Tc, and the ambient temperature maybe is the T, right? Then once T is not equal to Tc, then there's a radiation, okay, or transfer of the heat through radiation, all right? So I guess all of you know what is radiation. For example, how to warm up your hand, all right? So you can actually you make use of a process of radiation, okay? So then another phenomenon for you to know is for certain type of material, especially the metal, liquid, right? So when temperature change, is geometry will change. For example, the length will change, volume will change, right? So this, for example, if only the length will change, for example, we just restrict the variation of this material, and this material can only expand its length, okay? It cannot expand in the perpendicular direction. Then in this case, we have this equation, okay? Variation of a temperature will make the length of this material to change. L0 is the initial length, okay? When temperature increase, then its length will increase. And this also applicable to liquid, right? Or in general, okay? Material can change its volume when temperature change, all right? So V0 is the initial volume, and the beta is a coefficient of volume expansion, right? So once we understand all these physical phenomena associated with temperature, then we can apply them to guide the design of temperature sensor, all right? So here I just list down 4 principles for measuring temperature. For example, we can make use of these physical phenomenon of volume expansion, all right, to design maybe the manual sensor for temperature. We can also make use of the difference in expansion coefficient between 2 metals, because one expands faster than another one. Then this difference in expansion will produce a deformation. Then we can use this deformation as an indicator of a value of a temperature, all right? Another phenomenon is if you put the 2 different type of a metal together, placed inside the same temperature location, actually you will produce a voltage, all right? So if we have a 2 junction of a 2 different type of a metal, one in the hot area, another is a cold area, then you will see a voltage or current pass through them. So that is another way for us to come out the design of a temperature sensor, or convert value of a temperature into voltage, right? And the last one basically is for you to know, it's like a thermistor. When temperature change, because when temperature increase, the internal energy of the material will increase. Then in this case, either the electron will move faster than the atoms nuclear, all right? Either one situation is the electron, okay, will be excited, okay, much stronger than the excitement of nuclear. Then in this case, the electron will easily move around. So it means what? Resistance will drop. Resistance means what? Resistance to the movement of electron, all right? So when the electron get excited faster than the excitement of nuclear, then resistance will drop. If the excitement of a nuclear will be much stronger than the excitement of electron, then resistance will increase. All right. Okay. So that is a physical phenomenon for us to come out the solution for the design of a temperature sensor. I guess this one, every one of you know that you can purchase from the shop, okay? And inside you will see we have liquid, mercury. Mercury is a liquid, all right? Then when temperature change, then it's a volume change, right? Then inside we have a tube, okay? Then we can calibrate this device. Therefore, then we can put the scale so that we can manually read out what is the temperature. For example, this is a 40 degree, 25 degree, 15 degree, 0 degree, all right? So we can calibrate this sensor. So you see, this is a manual sensor for measurement of a temperature. And you understand we leverage on the physical principle of making material to expand or contract, okay, by changing the temperature, right? So it's quite straightforward. Another principle is to leverage on the difference in the expansion coefficient between two metal, right? For example, the green one, okay, the metal in green color will expand faster than the metal in purple color. Let me say on top is a purple color, right? So when the green one expand faster, okay, or longer than the purple one, then when the temperature increase, then you will see these kinds of displacement, right? Deformation upward. Otherwise, there's a deformation downward, right? So then we can convert deformation into resistance. We can have a special material just convert deformation into resistance. And you may heard of a strain gauge for those of you, if you do not know, because we can place a strain gauge, okay, strain gauge here, then the deformation will change the resistance value of a strain gauge, all right, okay? And this is another application of making use of a difference in expansion coefficient between a pair of metal. But now, in this case, instead of linear, okay, alignment, okay, like this case, so we just put this two pieces of metal, okay, along a line or planar surface. Now here is in a helix form, okay, like a string, all right, a string, helix form. Then when the expansion is different, then it will produce a rotational motion. Okay, then in this case, if we calibrate the scale, then we should be able to get the reading, and this reading are related to the temperature. All right, okay. And some method is to leverage on this phenomenon. Two different metal, also the temperature are the same. Then it will produce a different voltage at this point. Then at another point, if there's a T1 is not equal to T2, then the voltage produced at the junction is a function of a temperature. When T1 is not equal to T2, then the voltage at the T1 will not be equal to the voltage at the T2. Then there's a voltage difference. So you see, this is a direct way to convert temperature difference into voltage. And if let's say T1 is a reference temperature, let's say 0 degree, all right, voltage, then the reading of V is indication of temperature, right? So it's quite straightforward. Okay, then you may say, okay, it's difficult to maintain 0 degree, right? Because we cannot design a refrigerator to make T1 to be 0 degree. Does not make sense. Otherwise, your sensor is too expensive. All right. How to overcome this problem? If let's say in practice, difficult to make T1 to be 0 degree. All right. Maybe T1 is any room temperature, right? Then in this case, how to make this one equivalent to 0 degree? The answer is what? Answer is, if let's say at the T1, any temperature, okay, you get the voltage, okay, a reading. Then we just supply negative value of a T1. then we get the equivalent 0 degree. That is this Joyin tell you, cold junction compensator. All right. So this is here is a T1 measurement downward. Here is T2 is NO temperature on the measurement. How to make this T1 to be equivalent to 0 degree? All right. The answer is we add in this compensation voltage. So this voltage plus voltage produced by the junction at the T1, add them together is equal to the voltage when this junction is placed at the 0 degree. That's it. Now you see this is a very cheap solution. All right. So no need for us to install a refrigerator here to make T1 to be 0 degree. All right. So you see, we have an engineering solution to achieve this assumption. So in general, we can assume T1 is 0. How come we can make such an assumption? Because we get A in VC. All right. VC plus T1 or VT1 is equivalent to the voltage when this junction placed at the 0 degree. That's it. All right. Magic. Okay. All right. And then in the video, you see, okay, the direct way, the most cheap, okay, the cheapest way, okay, for us to design a temperature sensor is to make use of this special resistor. And this resistor, we call it as a thermistor, all right? And normally, thermistor will have this property. When temperature increase, and the electron inside the thermistor will be excited, okay? Will feel excited much stronger than the excitement by the atoms nuclear, right? Therefore, the electron can easily escape, move around inside the material. So therefore, resistance will drop, right? So normal situation is like this, okay? So we call it as a negative temperature coefficient, all right? And then what is a resistor? It's very simple. It's just a special material just placed inside device. You see, is this all this material? Then you have an input, you have an output, then the current can pass through. That's it. Okay, design is very simple, right? Okay, and then how to convert resistance into voltage? Also, you know that, all right? So you apply a voltage, 6 volt here. Then you have a thermistor plus a normal resistor. Then here is the output voltage channel. Okay, then this voltage is related to the temperature, right? So it's very simple. Okay, so then in practice you can purchase all these thermistor. Okay, so it looks like in this situation. All right, and for temperature negative coefficient thermistor, so you will see these kinds of curve, right? So when temperature increase, resistance value will reduce. So it's easier to understand now. When temperature increase, then the electron has more energy than the nuclear, right? Then it's easier for the electron to move around. When electron could easily move around, it means what? Resistance value is small, all right? Okay, that's it. And if you want to do practice, here is basically is a scenario for you to leverage on the use of a microcontroller to come out the design solution of a temperature sensor. All right. Here is a microcontroller. I guess some of you may heard of this name, Arduino. Arduino is just one of the microcontroller, all right? And then you see with this sensing element or special device we call is a thermistor, and connect with a normal resistor. Then this is the way for us to convert it into voltage, because here is a variation of the voltage. Now you understand, okay, by default, microcontroller is a sensor for voltage, all right? So this is a typical scenario for us to achieve the design of a temperature sensor with the use of a microcontroller, right? Okay. Then for those of you, if you know the Arduino, then the design, the the detailed connection looks like this. All right, just follow this. Should be good enough. All right, but here we will talk about the in lecture 2. I will tell you how to make use of ARM Cortex M4 to serve as a general microcontroller, which could interface with all kinds of analog sensor. Right? Okay. Then, how's about humidity? Because in our room environment, temperature is very important. All right. Humidity also is important. If the room is very humid, you may not feel comfortable to live in a humid environment. Understand? So humidity is very important for human being. All right. But interestingly, humidity is also very important for the plant, for vegetable to grow. All right, so this video will tell you this story.
And today we're going to talk a little bit about humidity and controlling humidity in your greenhouse or in your warehouse growing operation. So the effects of poor humidity management is a lot of time when you end up with humidity ranges outside of the ideal. So different crops prefer different humidities, and they function differently in different humidities. Additionally, if you have different humidities, sometimes it impacts the final product, not just the growth of the plant. So it's really, really important to understand humidity, what your humidity is, and be able to manage your humidity within a certain range in the growing environment. So for most growing environments, optimal humidity levels for most crops. And today we're going to talk a little bit about humidity and controlling humidity in your greenhouse or in your warehouse growing operation. So the effects of poor humidity management is a lot of time when you end up with humidity ranges outside of the ideal. So different crops prefer different humidities, and they function differently in different humidities. Additionally, if you have different humidities, sometimes it impacts the final product, not just the growth of the plant. So it's really, really important to understand humidity, what your humidity is, and be able to manage your humidity within a certain range in the growing environment. So for most growing environments, optimal humidity levels for most crops will range between like 85% humidity and 60% humidity, somewhere in that range. Most crops fall in the 75 to 85% humidity range, ideally. But a lot of crops are very comfortable exceeding that. A lot of crops are okay going under that. So when things get too humid, and too humid again is a very subjective term, but if things are too humid and you're starting to see disease or fungal pathogens show up on your plants and you're struggling with some of these issues, you've probably got a bit of a humidity problem and you need to know how to dehumidify. There are a lot of ways to do this. If you live in a dry environment, then oftentimes air exchanges will take care of the problem for you. Or you can rely on air conditioning, which dehumidifies through kind of the by condensation. Or you can use an industrial dehumidifier or even a home and hobby dehumidifier for a smaller operation. So a lot of folks ask about cooling walls. Well, cooling walls, swamp coolers, that kind of thing, they work in really dry environments because they're dumping water vapor into the air, right? So that's why they work, which means that they're actually adding humidity to the air. That's typically why they're not super effective at very high humidity levels and why they work so well in dry environments. Those types of cooling things, typically, if you're growing in a greenhouse that uses the cool wall effectively, you probably don't have a humidity problem because you're already in a place with really low humidity. So humidifiers and sizing them can be a really tricky subject, especially when it comes to plants. In traditional engineering, they know how many people will be in a building exhaling. They know what the humidity level of your breath is. They know what the humidity levels outside are from season to season. They know all of the different things that are contributing to humidity in that environment. But indoor growing is such an early industry that it's really pretty up in the air as to how much water plants are oftentimes dumping into the atmosphere. So this can be a pretty tricky subject, but if you're already growing indoors, you know how much water your plants are consuming, right? Because you're having to top off your sump tank. The difference that you're topping off your sump tank, a significant amount of that is just transpirational losses from your plant. So they're just
okay. That should be good enough for you to understand. okay, it is necessary for us to control humidity in agriculture because the plant vegetable require humidity level between 60% to 85%. All right. Then for human being and even for animal, all right, the same situation because
indoor residential humidity, reducing humidity at the source, improving indoor ventilation, dehumidifying, and improving thermal window energy efficiency to prevent condensation. Condensation forms on cold surfaces as surface temperatures fall below dew point. Humidity increases with the amount of people and activities in the home. Showers, laundry, cleaning dishes, and unfinished crawl space areas can cause indoor humidity to be unnecessarily high. In conventional Canadian homes, it becomes necessary to reduce indoor humidity with the onset of winter. As a rule, 30 to 35% indoor humidity is recommended for -5 to -10 degrees Celsius. When tackling indoor humidity, always improve the areas where the moisture is being generated. Installing good quality bathroom fans and cleaning the unit seasonally will help keep the exhaust fans effective. Cooking range and other exhaust fans should be directly vented to the exterior and not into the roof perimeter soffit. If you have a forced air furnace, check to see if you have a fresh air intake. Fresh air intakes make all the difference in reducing indoor humidity in the winter. That is, providing that they are working properly. These units often require seasonal cleaning and should be located where good quality air can be drawn into the home. Fresh air intakes should be located well away from vehicle exhaust, pellet stove exhaust, and clothes dryer exhaust vents. You can monitor your indoor humidity levels with an inexpensive humidity gauge or use a wall-mounted dehumidistat switch connected to an exhaust fan.
Okay, so this should be good enough for you to know. Okay, in the living environment, then you see, for us, if the humidity is around 35%, we will feel comfortable. Now you remember for the vegetable plant, they like the humidity to be between 60 to 85%. Then for human being, it's around 30 to 35%. All right. So it's a different requirement. All right. So humidity control is very, very important for our daily life and also for agriculture. All right. Then what is a humidity sensor? So this slide showing you, this video show you example.
In this tutorial, we will learn how to use the DHT11 and DHT22 sensors for measuring temperature and humidity with the Arduino board. These sensors are very popular for electronic hobbies because they are very cheap but still providing great performance. Here are the main specifications and differences between these two sensors. The DHT22 is the more expensive version, which obviously has better specifications. Its temperature measuring range is from -40 to +125 degrees Celsius with 0.5 degrees accuracy, while the DHT11 temperature range is from 0 to 50 degrees Celsius with 2 degrees accuracy. Also, the DHT22 sensor has better humidity measuring range from 0 to 100% with 2 to 5% accuracy, while the DHT11 humidity range is from 20 to 80% with 5% accuracy. There are two specifications where the DHT11 is better than the DHT22. That's the sampling rate, which for the DHT11 is 1 Hz or 1 reading every second, while the DHT22 sampling rate is 0.5 Hz or 1 reading every 2 seconds. And also, the DHT11 has smaller body size. The operating voltage of both sensors is from 3 to 5 volts, while the maximum current used when measuring is 2.5 milliamps. Okay, now let's see how these sensors actually work. They consist of a humidity sensing component, NTC temperature sensor or thermistor, and an IC on the back side of the sensor. For measuring humidity, they use the humidity sensing component, which has 2 electrodes with moisture holding substrate between them. So, as the humidity changes, the conductivity of the substrate changes, or the resistance between the 2 electrodes changes. This change in resistance is measured and processed by the IC, which also makes it ready to be read by a microcontroller. On the other hand, for measuring temperature, these sensors use a NTC temperature sensor or a thermistor. The thermistor is actually a variable resistor that changes its resistance with the change of the temperature. These sensors are made by sintering of semiconductor materials such as ceramics or polymers in order to provide larger changes in the resistance with just small changes in the temperature. The term NTC means negative temperature coefficient, which means that the resistance decreases with the increase of the temperature. Okay, now let's connect the DHT22 sensor to the Arduino board. The sensor has 4 pins: VCC, ground, data pin, and a not connected pin, which has no use. A pull-up resistor from 5K to 10K ohms is required to keep the data line high in order to enable the communication between the sensor and the Arduino board. There are some versions of these sensors that come with breakout boards with built-in pull-up resistors, and they have just 3 pins. The DHT sensors have their own signal wire protocol used for transferring data. This protocol requires precise timing, and timing diagrams for getting the data from the sensors can be found from the data sheets of the sensors. However, we don't have to worry much about these timing diagrams because we will use the DHT library, which takes care of everything. Here's the Arduino source code. After we have included the library, which can be found from the Arduino official website, we need to define the pin number to which our sensor is connected and create the DHT object. In the setup section, we need to initiate the serial communication because we will use the serial monitor to print the results. Using the read22 function, we will read the data from the sensor and put the values of the temperature and the humidity into the T and H variables. If you use the DHT11 sensor, you will need to use the read11 function. At the end, we will print the temperature and the humidity values on the serial monitor. Here's the result that we will get after we will upload this code and run the serial monitor. I also made an example where I displayed the results on a LCD. You can find the source code of that example on my official page.
Okay, so this is a very good example which is showing you 2 things. One is a relationship between humidity and the temperature. And you see these 2 sensors is always coupled together. Later on, I will show you that the definition of humidity is a function of a temperature. All right, so this is why you need these 2 value in order to determine humidity. And the second interesting for you to know is to come out the design of a smart sensor. So actually, this sensor itself is a smart sensor. You can imagine that it has already a built-in a mini version of a microcontroller. So therefore, you just consider this sensor itself as a not inside IoT itself, all right? And then if let's say you have your own microcontroller, then interface become a exchange of data, because you see all these, you see you have a data line and you have supplied the voltage to the ground. So this looks like a serial communication protocol, all right? So you just leverage on the knowledge that you have learned in the last week, all right? Treat as a microcontroller plus temperature sensor, humidity sensor, and this is your microcontroller. Then you undertake data communication, all right? So this is a very, very good example for you to follow in case if you want just to develop a smart sensor, right? Just a sensor with microcontroller built-in, that's it. And the extra thing for you to know is about the program. Just now you see last portion is a program, all right? So if you are the designer of a smart sensor, you must offer a library function for the buyer of your sensor, all right? So that give you a very good example for you to know, okay? In order to develop a sensor as a product, what should be the tool, software tool that you are going to provide to your customer or to your buyer, right? Okay. So now we try to understand a little bit about the physical nature of humidity. Humidity basically refers to the phenomenon of presence of water vapor in air, right? I guess all of you know such a phenomenon, especially between the season of autumn and the season of winter, a that period of time. Then we see a lot of such weather condition, okay, a lot of water vapor inside the air, all right. And sometimes the highway will be shut down because it's very dangerous for people to travel at the high speed, etc. Right? And how come there is presence of water vapor in air? The reason is what? Reason is because any material could make a transition among these three states. Okay, material could be in solid state, liquid state, and the gas state, and they can make a transition among these three states. So for water, when water become a water vapor, the water vapor will mix up with the air, right? Then that create weather condition which will reduce visibility. When there's a lot of water vapor in air, then we cannot see far away. Another phenomenon is about this condensation, okay, transition or transformation from gas state into liquid state, right? And there's important terminology which is called as a dew point. Dew point is a temperature of a surface at which the vapor, the material in gas state will transform into material in liquid state, all right? And this dew point is not a fixed one. It depends on the temperature of the air and also humidity. You see this curve, let's say the room temperature is 30 degrees, for example. And if you have a surface, if the surface temperature is 5 degrees, and the humidity is 20%, then this 5 degrees is already a dew point, right? So then below this, okay, with 5 degrees or even lower than 5 degrees, then this surface will see the presence of a liquid, okay, because 5 degrees will trigger the transformation from a gas state into liquid state, all right? But when humidity increase, for example, this line now is 30%, then you see 5 degrees is no more dew point. Just any surface must have something like 11 degrees. Like 11 degrees then become a dew point, all right? As long as temperature is below 11 degrees, then this surface will see the presence of water vapor. So you see, normally in winter, you see the glass temperature is lower than the room temperature. This is why we see the presence of water liquid on the surface of glass, right? So that is this phenomenon. And this also help you to understand how come, what is a cloud in the sky, all right? Cloud in the sky basically is water in liquid state, but tiny liquid state floating in air. Now this slide help you to understand what does it mean by cloud, okay? Cloud basically is water in liquid state in air, all right? Then how come water will become liquid? The answer is what? Because on the ground, the temperature is higher, right? When we go up, okay, reach certain level of 4,000 feet, then you see the temperature in air is equal to it will be low, okay, 65 degrees Fahrenheit, okay, and then this is equal to the dew point temperature. Then at this point, the water vapor start to become a water liquid. All right, then we see the cloud to form. Okay, this slide help you to understand the answer. How come you see the cloud in the sky? All right, but actually we can make use of this phenomenon to purify the water. Let's say water here is not drinkable because of many other components there. How to obtain pure water? Answer is what? To have this condensator, because here you have a surface with a lower temperature. The temperature is below the dew point temperature. Then water vapor will become a water liquid. Then if the surface has this orientation, now you see with the pure water will appear in this side. Then we can collect the pure water. Then this side is drinkable water. All right. So you understand, we can make use of this process to produce drinkable water, right? And also we can use this process to harvest energy. It's like when we burn the gas to produce rotary motion into electricity, like electricity generator, and the gas. The output side still is very hot at the higher temperature. Can we collect this thermal energy? Okay, then first to produce steam. Steam will drive a rotary machine, then continue to produce electricity. So the answer is yes, right? So you see, we use a condensator to convert the water vapor. Here is a steam, means a water vapor into liquid. Then liquid pass through the tube here, then absorb thermal energy from the exhaust air. Okay, then absorb the thermal energy, then become steam again. Then steam will drive a rotary machine, then produce electricity. So this is to harvest the energy to make energy production more efficient, right? So then we may also see another phenomenon of transformation from a gas state directly into solid state, especially for people. For those of you come from northern China, in window situation, you may see the ice form on the branch of the tree or leaf of the tree. So that is a phenomenon of deposition directly transform from gas state into solid state. You see all the ice form on the leaf or the branch of the tree, right? Okay, something like that. And for those of you live in near the sea, okay, if you have a river, then you see transformation from a liquid state into gas state. So this process is called evaporation, all right? And the evaporation actually will increase the humidity. Now you understand how come there's a humidity in air. Answer is what? Because there is this evaporation. Evaporation from water in the river, water in sea, or water from the body of animal, like a human being also, all right? So for example, the outside temperature is higher than our body temperature, then our body will trigger the process of evaporation, all right? So you see the evaporation, all right? Okay, so that increase the humidity. Then immediately understand that when humidity increase, visibility will reduce, all right? Okay, so it makes sense, right? Then we want to know how to convert the value of humidity into voltage, all right? Now you see the solution is what? Solution is to convert humidity into value of resistance. Then value of resistance could be converted into value of voltage. Once we have the voltage, then we can use a microcontroller to do the measurement, all right, to do the reading, produce the reading, all right? So then the easier solution is to make use of this phenomenon called as moisture. Okay, in the video you see this moisture. Okay, the moisture means a material in a solid like a tissue absorb a lot of water, then the moisture level will increase. When the moisture level increase means what? Resistance level will reduce, because moisture is electric. It has a higher conductivity of electricity, right? So, and then this showing you the design of the device which for us to convert either, okay, humidity into resistance or humidity into capacitance. Okay, for those of you, if you can remember, what is a capacitor? Capacitor consists of two parallel plates. By default, inside is the air, but we can insert, okay, other material, right? So this material is not, we are not, okay, let the current to flow from one parallel plate to another parallel plate, all right? But this material, if has a high level of moisture, okay, when the moisture level is higher, then he will increase capacity to attract the electron, okay, inside the capacitor. Then capacitance will increase, right? So this is another principle for us to convert humidity into capacitance, and then capacitance into voltage, right? So then this showing you example. When humidity level increase, the moisture level will increase. When moisture level increase, capacitance increase, right? That's it, right? Then we may want to know what is a humidity, okay? The easiest way to define humidity is this equation, okay? It's just to calculate the presence of water vapor per unit volume, all right? So the mass of a water vapor divided by volume basically is the presence of a water vapor per unit volume, okay? So this is a definition, strict definition of absolute is a humidity. However, this is not intuitive, all right? Because we have no idea about the unit, like you may say 0.5 gram of water. It's not intuitive. So actually, we may have another definition, that is relative humidity. Relative humidity is easier. We may say, okay, what is the situation of 100% humidity? For example, in the room, we may remember, this I feel this is 100% humidity. And when there are less vapor, then we may say now is 50% humidity. Then our body can easily remember all these measurements, all right? So this is good in mathematics, but not good in practice. So in practice, we use relative humidity, all right? But with this mathematical definition, we can relate, if let's say we treat the air as an ideal gas, then we have this equation of absolute humidity. So it's quite easier for you to understand. So N is a Mole number. Mole number means the mass of a gas divided by the molar mass of a gas, all right? So then from this this equation, then you have an equation for us to calculate what should be the humidity, all right? But just now I mentioned absolute humidity is not easier for us to remember, but relative humidity is easier for us to remember. For example, inside the room, a room can only reach a maximum humidity. It's always a fixed level. The maximum amount of water vapor you could be present inside the room is a fixed number. So therefore, we can remember the worst situation in terms of humidity. And when humidity drops, then our body will feel comfortable. Then our body can remember. So use this one. That means we use the maximum humidity as a reference, just compute the percentage, all right? So, and normally should be less than 100%, right? So then we can also come out this equation, because in the worst case situation, what should be the maximum amount of the mole number, okay, or molar number of water inside a volume, all right? Then what is the actual molar number inside the volume? Then compute the ratio. Let's say that give us a relative humidity, all right? Then here is a comparison. In the room, you may feel, this is a 95% humid. Okay, your body may memorize the feeling, right? Now we say, now is a 10%, you feel comfortable, right? So our body can also memorize such experience, all right? So it's more intuitive, right? Okay, and this just for you to know when temperature increase, all right? When temperature increase, you see this equation, the maximum pressure will also increase. if the volume is fixed, so therefore the humidity, relative humidity will drop. All right, for example, 100% humid, once we increase the temperature, we feel better, all right? The relative humidity will drop, all right? Okay, and especially it helps you to understand how come in winter we feel humidity. The weather is cold, we feel humid. Now you understand, because when temperature go down, with the same amount of water vapor, relative humidity will increase, all right? So that help you to explain how come in winter we suffer humidity, all right? Okay, with this understanding, now we know how to convert, all right, humidity into voltage. And also we know humidity is related to temperature. Here also telling you humidity is related to temperature. So this is why when you design humidity sensor, must always incorporate temperature sensor. All right, so you understand, okay, the situation. And how to convert humidity into voltage. So two popular methods include, one is to convert humidity into resistance, like resistance into voltage, all right? And then you get this kinds of relationship. And here is an example, of a product, all right? And then you can use this device to incorporate into your smart locker or humidity sensor, which could be placed inside your room environment to monitor the room's humidity. And the second popular method is to convert value of humidity into the value of a capacitance. Then from capacitance, we first convert it into voltage, all right? In case of a resistance, higher humidity, lower resistance. But in this case, higher humidity and then higher capacitance is because the moisture level inside we call it the dielectric material between the two parallel plates inside the capacitor, right, will increase the capacitance, all right? So this is this phenomenon. Then in this case, okay, you can incorporate temperature sensor together with your humidity sensor, all right? And you can also come out a solution to make your temperature humidity sensor to behave like a smart sensor. So you see here, you have a humidity sensor, you have a temperature sensor. Actually, after that, you see a mini version of a microcontroller. Then once you have a smart sensor, then this sensor will output digital data in the form of a stream of a bit or stream of a byte, all right? Then you just treat it as an independent node inside your IoT, that's it, all right, okay? And this slide showing you some popular product in the market for humidity sensor. And here I just want to highlight this information for you to know the slow response from humidity sensor. You see, it may take 15 seconds, sometimes 120 seconds, a few minutes, all right, to respond, all right, because the moisture level need to take time to build up, all right. So it take time because it is a slow process for water gas to water vapor to become a water liquid. It's a very slow process, all right? So that's about the analog sensor. Then how's about the velocity sensor? Just now I mentioned, just remember, all right? Microcontroller by default is a sensor for measurement of a voltage. It is also a sensor for measurement of velocity of a square wave, right? If we can convert velocity of a rigid body into a squared waveform, then we can measure velocity of a rigid body. That's it, all right? Then what is velocity of rigid body? I guess all of you know, all right? When you walk, then when you see something rotate, and then when you move your body, actually there's a velocity, okay? So it's very easier for you to understand. Then the question is how to convert, all right? Rotary motion or linear motion into velocity of a square wave, okay? So Actually, there's an easier solution, all right? So we just use a pair of a light emitter, light detector. You see, transmitter, receiver is a pair. But here you will see we use a 3 pair. Later on, you will understand. Okay, in the simplest way, you may say 1 pair good enough, all right? Just convert the absolute value of velocity of a rigid body's motion into the velocity of a square waveform, all right? From then why do we need to have an additional one? Then why do we need to have another additional one? Later on, we'll tell you, because we may want to know the direction of the motion. Then in this case, we need to have a pair of square waveform in order to know not only the value of a velocity, but also the direction of the velocity. Then how about the third pair, third one? Third one is for us to know the 0 position or the starting point when velocity occur. Then we can do integration. I guess all of you know what is integration. Integration of a velocity give you result of distance, yes or no, position, right? Integration of velocity equal to position. That's it. But this integration must start from 0, T0. How to know T0? That is the third pair of light emitter, light detector. That's it, all right? So when it's rotate, then you will see, and you have a lot of series of a hole. When the light can pass through, then you have a positive pulse. When the light cannot pass through, there's no pulse. When this rigid body rotate, it means what? Then you, from the receiver, you will see a string of square wave as output. That's it, all right? So then we achieve the goal to convert the motion of a rigid body into the velocity of a square wave. That's it, all right? Then microcontroller is by default a sensor which can measure velocity of a square wave, right? Very simple, right? Okay, then how about linear motion? For linear motion, is the same now. Then you see on top we have a transmitter, at the bottom we have a receiver. And here you only see 2 pair. 2 pair is needed for us to know absolute value plus direction of the motion, all right? If we want to know the 0 position when the motion occurs, then you need to have a third pair to indicate 0 position. Therefore, you can do integration, all right? Okay, so then how to know the value of a rotated angle, all right? Because between 2 adjacent hole, there is an angle, theta p, we call it the pitch angle, right? So if we count, let's say 100 pulse, 100 pulse times this one, then give us reading, right? That should be the rotated, okay, angle. But some of you may ask this question, if you put yourself as a student, then you say, theta p, in this case, it looks like a few degree, big error, right? And normally we will measure the velocity at the output at the high speed end, because normally we will put a speed reducer. Speed reducer, that means it's a normal output of a velocity. Normal output of a velocity come from a high speed source of a velocity. And in between, we have a speed reducer, right? Speed reducer in mathematical term is input velocity divided by the reduction ratio. And the normally reduction ratio could be 1,000. Now you see, if let's say 2 degree of error divided by 1,000, it's very small. All right, that answer your question. So you should not worry about the okay, big error. Actually, it's not. Once you have a practical implementation, usually we'll put the speed reducer. The speed reducer will give you a value of a divider of 1,000, divide by 1,000, then you can ignore the error. All right. So okay. So that give you, okay, this is an exercise for you to know what is the pitch angle. It could be 1.8 degree, 2 degree, and then you may say, wow, this is a big error. Actually, it's not. Okay, 2 degree divided by 1,000. Okay, negligible. All right. Okay, and once you see there's a light emitter, light detector, when it pass through the hole, then you have a positive pulse, all right? Another one pass through, another pulse. Then this is why we have a square waveform. Then we just measure velocity of this square waveform. Then done already. Then we can measure velocity, right? Okay, so this is an example. Then we can set the time window. We do the measurement within a period. Theta t is a period, right? And then we can count the number of a pulse. How to measure the velocity of a square wave? Basically, is a counter, okay, to count the number of a pulse, all right? And this is exercise for you to know the mathematics, all right? If let's say we have a 500 pulse within 10 milliseconds, then we can calculate what is average velocity, etc. Right? Then here you may ask question: how come we have a 2 pair, 3 pair? 2 pair A, B is for us to know direction of the motion, and the R is for us to know zero position, right? So if we undergo, let's say, clockwise rotation, then we have a 2 square waveform like this. Then here we say A will lead B because signal from A come first, followed by signal from B, all right? But counterclockwise rotation, then you will see signal B will lead signal A. That means signal B come first, followed by signal A. Okay, so this is why you need 2 signal, okay, detected from the pulse. Okay, how's about the R? R is for us to know zero position. All right, then here is showing you the solution. Okay, so by definition, you see this is a definition of average velocity, and this is the equation of the measurement from the pulse. All right, because this is a theoretical result, this is a practical measurement result. So this must be equal. When they equal together, then you cancel out the theta t, and now our objective is to measure theta, and the theta I is a starting point. Okay. Because once you power on your sensor, so we have an initial position, but this one we do not know, because we cannot open the sensor to know what is the theta I, but it does not matter, right? So then from this equation, then we have this. Now from here you see why the third pair of light detector emitter is coming in. So we have a reference intact. That means we rotate. When the third pair of light detector emitter give us a positive pulse, then we memorize what is the reading from the counter. And this reading of the counter actually will support this equation. So this is reference position. Now we let, okay, this equation to minus this equation, then you will see theta I will disappear, right? So this is the equation of doing integration, actually, for us to determine a position from velocity. Now you understand? So integration actually is implemented by this equation, right? And we need to have a reference signal for us to know theta r and the CR, all right? Then subsequently, all the output from the sensor is theta minus theta r, all right? Since the theta r is considered as a zero position, then we have absolute position. That's it. So this is a mathematical equation which support the implementation of doing measurement of a position, right? And this is a small exercise for you to play, okay? You verify whether the equation is correct or not, all right? Then this is just a summary for you to know, okay, what is a clockwise rotation, counterclockwise rotation. If okay, in this case, let me see. Just now I explained to you reversely. For counterclockwise rotation, signal A will lead signal B. For clockwise rotation, signal B will lead signal A. All right. Then from here you will see when signal B lead signal A is a clockwise rotation. When signal A lead signal B, then is a counterclockwise rotation. And when one signal remain unchanged, another signal make a 2 transition from low to high, high to low, then there's a change of direction. And here is the same. Signal B never change, but signal A changed 2 times. Then we know there's a change of direction, right? So, okay, so that's all. for this lecture one. So in lecture one, we have studied two types of sensor. These two are very popular, right? So first type are analog sensor. Second type is a kind of a digital sensor, right? For analog sensor, the idea is to convert the value on the measurement into voltage, all right? For digital sensor, the idea is to convert the value on the measurement into square the waveform. Then we just measure the velocity of a square the waveform or position of a square the waveform, all right? And this slide show you a hand-on practice in case if you have the hardware, then okay, so you just follow this one to do the connection, then can set up an experiment, all right? Okay, so we take a short break of 5 minutes. Then we continue with lecture 2. So we start at 3:30, all right?